to sort of hear that radio pulse. And if you kind of listen to the audio version of a pulsar, it'll make a kind of type noise. At least the fast ones make that kind of noise as you kind of hear that that radio pulse, kind of from the beacon that's kind of the spotlight that is hitting in our direction, so to speak. So, okay, there are a bunch of pulsars that rotate rapidly. There are pulsars that rotate even as fast as 1,000 times a second. The original pulsars that was discovered in 1968 are pulsars that were periods of around a second, I think. People thought it was really weird when they first discovered pulsars. It's like, this must be a beacon from extraterrestrials, because what could possibly make this sort of periodic signal that quickly? And then it turned out it was just physics, just a neutron star. Whether you decide that a neutron star is really like an example of extraterrestrial intelligence, that's a different issue. But it is, at least we can account for it in physics, as perhaps we can account for what happens in our brains physically as well. In any case, pulsars, they have this feature that they they produce these beams of radio energy, and they're spinning around very rapidly. You know, a pulsar is a neutron star is a collapsed star. So you take the whole mass of something a bit heavier than the sun even, and you crush it down into something that's 10 kilometers across. It's the density of an atomic nucleus, around 10 to the 14 times the density of water. And that thing is a very, you know, it's like a top spinning around, and it really spins very accurately. And so the timing of pulsars is very accurately determined. Sometimes there are kind of sort of quakes in the neutron star. The neutron, you'll get the analog of earthquakes in the neutron star, and those make little glitches. But basically, the timing of pulsars is very accurate. But if the structure of space is deformed so that you have sort of a gravitational field goes through, when gravitational fields, the presence of a gravitational field changes the rate at which time progresses. In our physics project, we can kind of understand how this works. It's kind of when there is sort of more gravitational field, more curvature in space, gravitational field associated with curvature in space, there are more updates to the structure of space to maintain the structure of space, then you can kind of then effectively the rate at which time is perceived to progress goes down. And so the same thing happens for a pulsar, that when the gravitational wave goes through, changes the gravitational, it changes the amount of gravity, so to speak, changes the effective way in which time passes, and it will change the rate of the pulsars, the rate at which the pulses come from the pulsar. So there's this experiment was done over the last 10, 15 years that recently announced some results, although the results were not as clearly kind of enunciated as one might have hoped, that that somehow we're looking at, I don't know, 60 or so pulsars at different places around the galaxy, that one could tell that there were gravitational waves that were of low frequency, very long wavelength waves, were just like a giant water wave that kind of slowly changes from being a crest to a trough and so on, that these were kind of going through this array of pulsars and showing gravitational waves. So the thing that the question is, okay, if there are low frequency gravitational waves, where did they come from? Did they come from the early universe? Most likely. Were they the result of kind of the fact that the early universe wasn't a perfectly spherical kind of thing? It was a thing that had kind of imperfections, and those imperfections led to things like these gravitational waves. Well, I think in our physics project, one of the things that's really sort of different is the idea that space is not just a three-dimensional thing, that the dimension of space is a dynamical variable. Space, in our view of things, in the case of general relativity, space got enough structure to have things like curvature. In our model, space really does have structure all the way down. It's like a fluid like water that's made of molecules. In our case, space is made of atoms of space. It's a giant network of atoms of space. And actually, the thing I have projected on the screen behind me here is a very toy example of kind of a network that represents the potential sort of connectivity of atoms of space. One feature of networks like that is they don't have an intrinsic dimension. They don't have there are X and Y and Z coordinates. Rather, starting from a given point, you can say you can kind of go out on the network in different directions, and you ask the question, how many places can you get to when you go a certain distance out on the network? And depending on sort of how fast that grows, that gives you a sense of the dimension of the network, but the effective dimension of the network. But the dimension can change. And so, for example, in the early universe, we think the dimension started essentially as infinite and gradually kind of cooled down to being the 3 dimensions that we now observe. And I think that that phenomenon of the sort of the cooling down from this infinite dimensional state, there are undoubtedly dimension fluctuations left over. Places where, you know, the effective dimension of space-time is 3.01 or 2.99 or whatever. And I think it is quite likely that there is a way to detect that fact, the idea of dimension fluctuations, if they're on sort of the same kind of length scales as the kinds of gravitational waves that are detected by the pulsar timing array, that it is quite conceivable that one might see the effects of dimension fluctuations in a case like that, which would be really exciting. And really, you know, the thing that we're, you know, there was this argument for so long about whether matter was discrete or continuous. That's an argument that went on from antiquity. And that finally that argument got resolved at the beginning of the 20th century, basically, by observing little things like Brownian motion, where you can, in some water or something, you have little pieces of that come from pollen grains, and under a microscope, you can just see things discretely kicking those grains around, and those discrete kicks are individual impacts of water molecules. And so we can tell from that, that's kind of the final thing that says, yes, you know, water is made of discrete things. It isn't a purely continuous fluid. Now the challenge is, can we see the same thing for space-time? We believed forever that space-time is basically continuous. Can we see the analog of Brownian motion in space-time? And that's kind of a big challenge. That's the thing that is really interesting to try and see with our models of physics. I think, you know, it's if we see dimension fluctuations, we see kind of discreteness, evidence of discreteness in space-time. I think, I mean, I have to say that for me, our physics project has fit together so elegantly that I just, it's sort of an inevitable thing. It has to work that way. But I think in terms of the kind of, look, you know, here's an experiment that you just can't explain any other way. The observation of discreteness in space-time, sort of an analog of Brownian motion in space-time, the analog of the observation of dimension fluctuations will be very striking. And, you know, we don't know how big the dimension fluctuations will be, just like we don't know how big kind of the other things left over from the early universe, how much variation in the density of things or the curvature of space-time or these gravitational waves we left over from the early universe. We also don't know what kind of dimension fluctuations will be left over. So we can't predict that, but even the very phenomenon of a dimension fluctuation is totally weird from the point of view of normal kind of thinking about physics. I mean, it's kind of like if you do calculus, you know, which is sort of the study of how things change and so on. You might do univariate calculus, one variable, one thing is changing. And then you might, if you do a more advanced class, you might do multivariate calculus, where you talk about, you know, X and Y and Z can all be changing. But what you never get to talk about is fractional dimensional space-time, fractional dimension, fractional number of variables, so to speak, where you have not X and Y and Z with 3 variables, but you have 2.95 variables. That's just not something one gets to talk about. It's something for in our physics project that we're working hard to try and sort of build the mathematics to understand those kinds of things. So let's see. Question here from Dugan, also in person. Can you discuss the next evolution for AI models? So far we have language models, image to text, text to image, etc. I think the next really obvious one is video. And, you know, one's starting to see some experiments with that. There's an awful lot about sort of how the world works that is captured in gazillions of hours of videos that are available. And I think that will be a place where one can learn things about how the world works that have not been readily learnable from text. You know, a picture is worth more than 1,000 words probably, and a video is worth even more than that. And I think that will be a big, big thing. Video generation will also be a thing. I think Exactly how that will be used, I'm not sure. I mean, people think about, like the Apple headset thing has this way of detecting, has cameras, inward-facing cameras that can see your eyes and so on. I think they have a plan that they announced to have kind of video conferencing where both people are wearing these headsets. And so if you looked at them in reality, so to speak, and outside from a camera, you'd see these people with great big headsets on, but you can kind of synthesize something that's kind of like what that person's face will be looking like just by those inward-facing cameras, even though there's headset over a bunch of parts of that face. I don't know how weird that will be and whether that will be wonderful or just weird. I think that, so video generation, there are surely lots of examples where that will become a thing. I mean, I think the thing to understand about something like video is it's kind of like the progressive evolution of user interfaces. In when we first started dealing with computers, we had just textual interfaces where we typed certain commands. Then we got things like graphical user interfaces where we were kind of looking at where we were having menus and we were being able to select things and so on. The thing that is sort of dramatic with large language models and ChatGPT and so on is this idea of a linguistic user interface. We, I would say, kind of pioneered that with Wolfram Alpha, where you could have, in Wolfram Alpha, you can ask a short question in pure natural language and have it converted to computational language and then answered. But ChatGPT and so on can deal with generating large amounts of text and potentially breaking down a large amount of text to see what were you talking about. So this kind of idea of a LUI, a linguistic user interface, is something that's kind of a new thing made possible by LLMs. So I'm sure that there'll be, VUIs, video user interfaces, so to speak, where both the input to the machine is kind of a video of you yakking as I am now at the machine, and the output from the machine will be a generated video of some avatar kind of talking to you, so to speak. And I'm sure that will come. I don't know, it's always interesting to see kind of how well that works. But that's the kind of thing I would imagine will come. Also, lots of virtual world kind of capabilities. I'm not sure, I think the jury is still out on how much people like virtual worlds in general. I think, post-pandemic, after we were all virtual for a while, I mean, I've been a remote CEO for 32 years now, so I've been sort of a little bit virtualized at the best of times, but we were all virtual for a while, and now it turns out, it seems like it's kind of fun to actually be in person, like at our summer school that we're doing now. And I'm not sure that the everything's going to get virtualized and generated by AI for videos and so on is necessarily the thing people are going to like. I mean, the thing we have to understand about sort of the progression of AI is much is computationally possible, but only a certain amount of that is what we humans care about and feel comfortable with. I mean, we can go out into the sort of computational universe of possible programs. We can make all kinds of stuff, like the thing that's behind me, for example. But then you say, well, is that a humanized thing? Is that something that sort of relates to something human? And it may or may not be. And sort of the question of what works for us humans as a kind of human user interface is something that kind of it's a different kind of question from what is computationally possible. So I mean, I think there's that side of things, the video user interface that will come. I think eventually there'll be neural user interfaces from various kinds of neural implant like things, and that will be a whole nother area. That one of the things that's already being done to some extent with machine learning is if you sever some peripheral nerve, you can end up with being able to have some sort of learning of what to do based on nerve signals from that. And I suspect that eventually there'll be those kinds of things. That's a sort of a different level of user interface. So I think those kinds of interfaces will be there. Another big area is robotics and actually being able to actuate in the world, so to speak. I would say two things. But first, actuating in the world, actually wandering around, sort of seeing the environment, having LiDAR and things to figure out the three-dimensional structure of the environment. That's one thing. The other is sensor nets in general. I mean, we, with our human senses, we're used to being kind of in one place. We've got our ears, our eyes, they're kind of within a few centimeters of each other. And we get to sense certain kinds of things. We have a certain amount of sort of distributed sensing from touch on our skin and things like this. But you can imagine, a sensor network where you've got 1 million sensors distributed on over a 1,000 square mile area, and they're all picking up different kinds of things. And that's kind of like a way. It's like a skin, like the touch sensors on a skin, but they're extended out over 1,000 square miles. And that's a thing from which we can learn, kind of our sensing of the world becomes a different kind of thing when we have those kinds of inputs. And I think that's another thing we'll see. Kind of, we don't completely know what to do with those things, and kind of understanding how that works is another thing that I suspect is coming as a domain for AI. I mean, I think in general, the story of sort of AIs like large language models is, so what's the normal thing to have happen? So in a large language model, you might have a prompt, and then you're asking, well, what's the normal thing? What's the reasonable text that you might continue that with? And that's kind of the story of many types of uses of large language models and AI and machine learning in general, is kind of what's the reasonable way to continue things. I think another type of, and so the same is true with videos, with the kind of in the sensor case, again, it's kind of like, is that surprising or not? The fact that something weird happened, that these sensors recorded this value, is that surprising or not? What can we learn from that? I think another place where kind of AI is an interesting question, how it's going to work out, is in kind of doing sort of natural science kinds of computations of what's going on, like an example being protein folding, where it's not obvious that the way that kind of a protein folds up is something that there's any reason to think that, for example, a large language model should have anything to say about it. I mean, a large language model, a neural net, it's based on the same kind of sort of fundamental architecture as our brains, and it's something where it's kind of got these neurons, just like our brain has neurons in it. And so the things that we can do, like produce language or recognize images, it's sort of unsurprising that we're able to do that with an artificial neural net. It's a very non-trivial scientific fact, because it shows that, if we want to know what's really going on in the brain, there isn't stuff going on that is sort of bizarrely different from the things that we capture in artificial neural nets. But when it comes to using these neural nets to do things like figure out how proteins should fold, why should that work? It's not obvious it should work. It's not obvious. I mean, there are sort of funny kind of self-referential explanations, like the things we care about in the folds are the things we notice in the structure of the protein, and those are sort of determined by our minds, by our brains. I'm not sure that's quite what's going on. I think it's just that these neural nets are pretty good at kind of just sort of filling things in so it's kind of smooth in some sense. And that's kind of a good way to take, I mean, in many cases, in the case of protein folding, what one's doing is one's saying, let's look at the 100,000 proteins that we know how they folded up. And let's take the protein where we're being asked, how's it going to fold up, and figure out what pieces of that protein correspond to the pieces of the protein, the 100,000 proteins that we know about. We know how those pieces fold up. Now let's kind of smoothly interpolate those things together. And that's really what the machine learning is doing. But, there are many other cases, like kind of mathematical calculations, where we're asking the question, if we're studying the solution to an equation that might represent a wave or something like this, or might represent, then the question is, how does that, is there a way of kind of shortcutting the kind of big computations that one might do there by just saying, well, let's see whether neural nets can figure it out, kind of like a human might say, oh, I've seen something like that before. It kind of reminds me of weather forecasting, where kind of the traditional version of weather forecasting back in the day was a meteorologist would say, oh, I've seen a cold front, a hot front, etc. I can kind of match the pattern of what's going on. This is what I think the weather will do. That kind of gave way in the 1980s and so on to the idea, let's just go solve the fluid equations on a supercomputer and see what the weather is going to do. And that worked very well. Now you can come back and say, well, actually, let's not do that. Let's just look at historical data about weather, and let's use machine learning to predict, based on that sort of historical data, what's going to happen next. I would say that's probably an intermediate case where it's not obvious which one is going to win. I think there are other cases where it's very clear that the kind of computational side of things is going to win. Other cases, it's very clear that the kind of just learn it from the examples side of things is going to win. You know, I think the another case people think about, is in mathematics. Now, mathematics is a case which is quintessentially computational, so to speak. You know, you want to figure out how do you derive this theorem from these axioms and so on. Well, there's a computational process. It's kind of a thing where you have precise rules, you just follow through those precise rules and so on, and that's how you figure it out. That part of it, I think, is deeply computational and is really not sort of an AI-ish kind of thing. I think the part that is more AI-ish is, okay, you can go out, you can figure out sort of all the possible theorems you could make. There's sort of an infinite number of possible theorems that are correct theorems of some particular area of mathematics defined by certain rules and so on. The question is, which theorems will we humans care about? And that's a question that is much more in the kind of the neural net, do something that's a sort of a model of a human kind of thing to figure out what happens with. And so that's a place where I kind of think that guiding sort of the you know, what theorems do we care about is more likely to work. Now people wonder about whether it's possible, you know, when you do sort of theorem proving and so on in an automatic way, there's kind of many paths you could take, and it's like, do you take the correct path, and can you guess by sort of intuition, by heuristics, by experience, can you guess what, you know, what path is the right path to take? And that's something which I would say I consider the jury is still out on whether that's going to work or not. So Dugan had also asked about training multimodal AI models. I think one of the interesting things there is there an intrinsic notion of meaning about things that is independent of the way in which we sense those things? So we see, we hear, we read a concept, a dog, whatever else. Is the intrinsic dog meaning something that is somehow encodable in a neural net or in our brains in a way that is independent of the mode by which that meaning came in? My guess is yes, there's a reasonable way to have a kind of a multimodal kind of representation of a dog or something. Now, you know, then you ask, the next thing that's sort of the feature of neural nets is, neural nets are an idea where you grind up any data you have and you turn it into arrays of real numbers, arrays of continuous numbers. In the whole idea of computing has been, you take everything in the world and you turn it into collections of bits. In the case of neural nets, you're sort of more specifically thinking about sort of these arrays of continuous numbers. And the question is there, when you sort of break things down from all these modes of input and you make them into this kind of inner core meaning, is that meaning, is the kind of representation of that core meaning in terms of arrays of numbers, what is that like? Is there something where you can say, well, I'm going to change these numbers just a tiny bit, and it's going to change the meaning only a tiny bit? Or will it be the case that you change some of these numbers, it'll suddenly jump from being a dog to a cat? I just was studying this a little bit, and there definitely are jumps. But it's an interesting question, what the kind of structure of that meaning space is. And for example, I've just been talking about what I call interconcept space. If you think about all those different possible meanings represented by these neural nets with all the different numbers in them, there's a place where those numbers correspond to the cat concept. There's a place where those numbers correspond to the dog concept. But then there's an interconcept space, just like we have interplanetary, interstellar space and so on. There's a place between the features we know, that's kind of interconcept space, where we have things which we've never seen before as humans. They're things that were not concepts we've ever come up with, but they're things that we kind of see on the journey from one concept we know to another concept we know. And exactly how that works, what's on that journey, are there big surprises on that journey that are very different from the things at the ends? Well, I've been studying that a little bit, and it's a little, there are some surprising things. There's some things that are very hard for us humans to interpret, and we don't really have we're at a loss for words, and that's not surprising because we're in interconcept space and the concepts correspond to words, and we're in a place where there aren't yet words, so to speak. So let's see. Daniel asks in person again, do you think we have reached a point of singularity such that any child born from today onward will never be able to surpass AI at any intellectual task, i.e., are we the last useful generation? Interesting question. I think that, here's the thing, the computational universe is very infinite. You know, we talk about that in our physics project in terms of the Roolead, the kind of entangled limit of all possible computations. That's kind of what's there of computational possibilities is very infinite. It's also, in a sense, it's both infinite and nothing, because it is everything, so to speak. It's sort of both the representation of everything, and therefore, in a sense, there is nothing unique about, well, it is a unique thing, but there's nothing that we can carve out of it and say, you know, kind of that's our special thing. I think the role that we humans have with respect to this sort of computational universe, with respect to the Roolead, for example, is to say, what are the things that we humans care about? We each have a certain thread of experience that is kind of what our mind follows through time. And I think that's the thing that is sort of the unique and significant thing about us, is our kind of thread of experience. If you say our experience will be generalized to everything, we no longer have this kind of coherent existence as entities, so to speak. So I think when it comes to the species as a whole, there's this question of, there's a lot of stuff that's computationally possible. There's the choice, the unique and perhaps significant choice of what parts of what's computationally possible do we explore. And I think that's the place where I think, you know, we humans still necessarily have a place. The Roolead is out there. It's doing all possible computations. It's already won the game. It's already doing everything. There's nothing, whatever we might do in our kind of development of our civilization and being more computationally sophisticated and so on, that's already happened. The Roolead is already out there doing all those things. So we are, the thing that we have to provide to it is merely that our thread of experience, our place, you know, we are uniquely visiting those parts of the Roolead that we visit, and that's significant to us. That's kind of the key thing that we're providing. Now, you see that at a very practical level. You see kind of when it comes to, you know, jobs people do, you know, there'll be a wave of automation that comes through where some job, people always used to be plowing fields or whatever else, and everybody kind of had to plow fields. There are a lot of fields to plow, but then that got automated. And instead of everybody turning to doing another thing, what instead happened is a great variety of different tasks got done by people, as if what was happening was that the frontier was always people picking what parts of what's possible they were going to pursue. And I kind of think that will happen again as we see sort of more automation. There'll be more kind of a sort of choice about what we choose to do. Now, remember, we already lost the game in some sense, or the Roolead already won the game, because it's doing everything. And that's, you know, when our sort of future of our civilization, we gradually get to sort of explore more and more of this Roolead, but it's already doing everything. So the thing that is going to be significant to us is the things that we choose to explore, so to speak. So I think it's a thing where the usefulness of us humans has to do with our particulars of history, so to speak. It's not the case. There's no sort of perfect sort of future of humanity that gets to sort of be everything. You know, by the time you are the whole Roolead, you are in a sense nothing interesting. You're you know, there's nothing special, so to speak. So I think it's kind of a what is significant in the future becomes partly a story of the uniqueness of our history, and that's what is significant to us. Now, you can say, well, I don't, you know, I want to just go general. I want to sort of go Roolead, so to speak. And then, well, then you've lost kind of the human element. And at that point, yes, it's kind of, you could say, well, we now know about the Roolead. We can just sort of hang up our humanness and forget that and just say, okay, the universe is doing its thing. You know, it's going to do everything. You know, no point in us being around, so to speak. But I think that's that's kind of my view of that direction. I think that you know, this question about to what extent kind of the intellectual tasks we do, I have to tell people who are actually here, if you're, unless you want to be on audio, you shouldn't make video. It's yes, now even more fun will be if we can actually do an interactive discussion, but I'm not sure we have quite the technology or setup to do that in a good way here. But in any case, Daniel asks, are we sort of the last useful generation because everything beyond us can just be done by AI? I mean, I think there's a way in which we may be a very, very useful generation in a different way, because it's a question of when more things become possible, when it becomes easier to do more things, there will be a question of, well, what is really the essence of humanity? What are the things that humans choose to do because they are constrained by sort of the features of the human condition? And now is the time when we're recording through live streams and many, many other channels, lots and lots about how we are choosing to lead our lives and so on. And that's the thing where, so we know a lot about the choices people are making today. And in the future, when people say, now we can do everything, so to speak, what should we choose to do? What would the actual humans do? Then it may be that we end up looking back at our times. I mean, it's not dissimilar to what's happened in the past with kind of lots of religious texts that came from a few thousand years ago, where people said, at those times, people really knew what it was like to be human, so to speak. Let's look to those kinds of lessons, so to speak, for what happens today. Let's see. Izero is asking remotely, is VR the future of UIs, of user interfaces? I don't know. I think my impression is that this kind of the whole headset thing, it's very dependent on how good the hardware actually is. Whether the thing really works, it's kind of like, doesn't do you any good to have a telephone if nobody can really hear what, if you keep on saying, what did you say? What did you say? That's not a very good telephone experience. It's not a very good, the early personal computers, the kind of the graphics was not I mean, at least for me as a kind of person trying to use these things, I wanted the big fancy computers because I wasn't going to be able to see very much on a little screen like that. My impression is that we probably reached the point where we have kind of a human vision level kind of access to displays, and that VR would be pretty useful for that in that regard. So for example, there's a question of how good does audio have to be before it's like as if you were there, so to speak. Our ears have like 50,000 nerve fibers going from our ears to our brains. Our eyes have like 10 million nerve fibers. You need a certain level of data going to your ears to be able to have audio that sounds like you were there. You need a lot more data to go from your eyes to your brain to have video that seems like you were there. And one of the big issues has been that we've got I'm distracted here because we're okay. One of the sort of big issues is our field of view. When we look at a display, we're just looking at this little thing that's in front of us. Our sort of natural field of view is much larger. And so one of the issues is sort of, can we have a display? And that was sort of a big deal with early VR, was we could actually have a head-mounted display where we actually saw out to, I don't know, 135 degrees or something, I forget the exact number, what the kind of, we could experience things, including our peripheral vision. And so that's a thing that now there are just about now high enough resolution displays that we can kind of feed every nerve fiber and get to the periphery of our vision, and then have an as if you were there kind of video experience. And I think that will probably be significant. And I do think that sort of the next generation of kind of VR, AR kinds of interfaces will be at least really good as a way to not have to have your computer screen sitting in front of you. You know, you'll be able to have your many computer screens floating in front of you. Now, I have to say, back in sort of in terms of future of technology, I have to say it was probably back in maybe 1979 that I first saw a window interface for a computer, graphical user interface for a computer based on Windows. I happened to visit Xerox PARC where that was being developed. And I was like, how can this possibly work? You know, you've got weird things like you're trying to move a file from here to here, and one window might be obscured, and then you can't get to the other one. You're going to make this whole mess of pieces of paper on a desk, and that was a really messy thing. And, you know, how can this possibly work? But I was wrong. It works pretty well. You know, now the question is, as we see the kind of, you know, in VR, we see kind of, you know, I've got windows all around me. And I've got, you know, all these, a window on the floor, a window on the ceiling. I've got little Post-its all around me, so to speak. I don't know what that's going to feel like. It might feel very messy, but then we're kind of used to that with sort of on-screen desktops and so on. I don't know. I think that there's a sort of interesting question. I thought about this like a decade ago, this question of how do you do selection? And, you know, do you do it with your fingers? Do you do it with your eyes? You know, I think in now there's pretty good eye tracking from and that will be a thing that will be significant, I think, in VR, is sort of how do you say, I want that thing over there? You know, how do we sort of point to it and so on? I think that's it'll be interesting to see how well that works. My guess is that there will be ways found to make that work really quite well. I mean, the idea of menus on a computer in the graphical user interface, that was an idea that had to be invented, so to speak. It required the idea of a mouse, a pointer of some kind. You know, these things had to get invented. Once invented, they turn out to be pretty intuitive. It's not obvious, you know, when you say, what are we humans used to doing? And you then say, well, what kind of interface can I make based on what we're used to doing? I think that's a more difficult thing. You end up inventing the interface and then people get used to it. I mean, another interface people have often talked about is kind of, as I kind of gesticulate around here, is kind of the gesture-based interface. It's usually, whenever people start talking about gesture-based interfaces, the movie Minority Report comes up, because that's a place where people really saw those gesture-based interfaces being used. I have to say, I'm not sure that I've yet seen kind of convincing use of gesture-based interfaces, but maybe with VR, with higher quality VR, that will happen. I think the real question is, you know, they're different things. Like, you know, I wear glasses. You know, the glasses are not cool in some way. But, you know, by the time everybody has an augmented reality system, glasses will be cool again. At least until there are kind of AR contact lenses or something like that. But, you know, and similarly, the idea of sort of going around with a great big thing on your head is kind of not necessarily cool or not necessarily comfortable to lots of people. And, you know, the question is, how good does it have to get before people are prepared to do that? You know, I myself have been, I've always liked to I walk around for, you know, a couple of hours every day. And I'm used to kind of figuring out, oh, I can have a treadmill where I have a computer and I can type on the computer while I'm using the treadmill. And back in the 1990s, I kind of had this vision where I'd be walking outside in a nice natural setting, and I would be using some kind of augmented reality, and I was kind of investigating chord keyboards as a way to be able to type while I was walking along. And, you know, it's now the 2020s, and we're not quite there yet. You know, the closest I can get is to have some kind of weird, you know, popcorn seller type rig where I have a computer on it and I'm kind of typing as I walk along, which isn't really so great. Or I can just be looking at a phone if I'm not the one typing. But I think finally, maybe within a year or so, maybe my 1990s vision, so to speak, of kind of going out and doing my walk with a whole AR system will actually come to fruition. I'm not sure if it may be one of these things of be careful what you wish for, because it may not work out as well as I kind of imagined in the 1990s it might work out. I would say also in terms of VR, I also, back in the 1990s, actually, when VR was sort of a thing back then, I mean, this is I'm talking about future of science and technology. For me, it's always very useful to kind of see something of the history of the future, so to speak, and knowing things which sort of seemed like, oh, this is going to happen. Or, oh, we saw it in the science fiction movies, it's going to be this way type thing. VR is a thing which, you know, seemed like it was absolutely just about to happen in the beginning of the 1990s, and it really didn't for reasons, I think, of technology and hardware and so on. And, you know, as you turn your head, can the accelerometer figure out kind of what you're doing from there? And I think that's sort of a thing where it gradually got better, so to speak. But this, you know, it's useful to see what happened to the things where we expected something to happen and then what actually happened. Often, to me, it's easier to see what will happen than when it will happen. And one can be off by many decades in when it will happen. And sometimes the question of when it will happen is a very contingent question. Oh, there was this particular person, there was this particular company, there was this particular rather bizarre business opportunity that made this be a thing right then, when it might not have happened until 50 years later, if left to other devices. I think one of the things back in the beginning of the 90s, I started thinking about kind of network-based models of space and the structure of the universe. And my immediate thought was, oh, let's use VR as a way to kind of pull through the cobwebs, so to speak, and kind of visualize this kind of network type thing. Still hasn't worked out. My experiments of about 3 years ago, when we were first launching our physics project with VR, were not very positive. It wasn't very useful. It wasn't something that actually fitted into at least my kind of experience of how things work. I mean, this is always the challenge, that you can invent some magnificent user interface which just doesn't happen to connect with humans. I mean, this is true with you know, we are pretty good with language. So when you come to a computational language which is written out in terms of word-like things, we manage to understand that. If your computational language is this complicated visual thing that's a network where everything's connected to everything and so on, we humans are not particularly good at that. It's not a particularly good way to provide a human user interface. You know, maybe it's a spider interface. If spiders are good at that, I don't know if they are, but you know, maybe there's sort of an alien intelligence where it is really good at sort of untangling those kinds of things, but we're not, so to speak. Let's see, there's a question here. Oh boy, we've got lots and lots of questions. Okay, another one from someone actually here, Michael. Given this is going to be a difficult one here. Given two contrasting scenarios of a pink plasma heaven where artificial general intelligence optimally solves problems for all sentient life, and a matrix hell where AI exploits humans as energy sources, how can we establish a guiding framework to navigate between these extremes? You know, I think this so-called pink plasma heaven that you're describing, where AGI solves problems for sentient life, I think that may very well be a be careful what you wish for kind of situation, because it's kind of one of these things where when there's nothing to do, things get very boring. You know, we humans have a certain human condition which has sort of certain, you know, we expect certain difficulties. If we don't have those, it's very unsatisfying. You know, it's kind of like I could just hang out and be happy, so to speak, but turns out that doesn't work that way. We even see that, I think, when a very sort of almost visceral level of people who do deep brain stimulation, and they're kind of trying to sort of solve problems for Parkinson's disease and things like that. You'll stimulate the brain, even right inside the brain in some way, and the brain will habituate to that, and it'll say, I don't care about that anymore. I want something new. So we are, for whatever reason of evolution, of biological evolution, what makes us sort of the human condition be the way it is, in part, is this desire to not have things be too easy, I think. So it's, you know, I kind of think that's to be careful what you wish for. Now, in terms of the AI kind of having its own objectives and saying, oh, those pesky humans, I can just use them as batteries, so to speak. I kind of think that's a wrong thinking scenario, because I think you've got to realize there's a lot that's computationally possible. The AI, the machines will run, they will do what they do, just as nature runs and does what it does. And the question is, you might say, is nature taking advantage of us? Well, you know, there are certain kinds of critters that wouldn't be happy critters unless there were humans that built cities and put garbage out and so on. It's, you know, nature at many levels is affected by us. You can ask the question, are we the victims of nature taking advantage of us? I think that it's kind of it's something where I'm not sure that it's, this description of a thing where the AIs are doing their thing and they're kind of taking advantage of us. I'm not sure that's a concept that necessarily makes perfect sense. I think that this question of, do the AIs do a lot of stuff we don't want them to do? Well, yes, that's an interesting and important issue. I've been thinking about that a bunch recently, of kind of how do you set things up so that you can make the AIs do the things we want and not the things we don't want. I think that at some level, the AIs become a bit like systems in nature, where they just do what they do, and we have to kind of do natural science to try to understand what they're doing. We have to try and fit in and figure out how we can find those caves to get out of the rain or whatever else it is. And we have to find ways to exist within this framework that is defined by sort of what happens in nature or what happens in sort of AI nature. But I think it's this question of sort of, how do we want to guide it? Where do we want to go? Do we want to go? We could decide in terms of nature, we could decide we really need to live at the bottom of the ocean. It's really hard for us to live at the bottom of the ocean. We'll get, nature is providing that possibility, but it's really hard for us to go there. I think sort of the same kind of thing can happen with AIs. There's a sort of a thing that is computationally possible, but it isn't a very good match for us, and we have a hard time kind of interacting with that. Let's see. Rob, also here, asks, does the structure emerging from the physics project give insight into the internal workings of LLMs? There's several people at our summer school working on kind of LLM science, as one might call it. Maybe it should be called AI science. I'm not sure. It's the natural science of LLMs. LLMs are weird things to do natural science about, because they're really pretty complicated. It's kind of like, what is the natural science of human knowledge, for example? That's been a thing about which there's been a bit done on the kind of global science of human knowledge. Aristotle was big on the kind of global science of human knowledge, inventing things like logic, writing down lots of encyclopedic kinds of things. We haven't been so, we've been much more of a specialized species, so to speak, more or less ever since. And so the idea of a global science of human knowledge has been something that hasn't really been thought that much about. LLMs kind of are front and center saying, hey, there is potentially sort of a global bulk science of things related to human knowledge, and it's a really interesting thing to study. Can our physics project help? I strongly suspect so. I think that when it comes to kind of what's the structure of sort of the space of what amounts to meaning space, what's the structure of the space that is created by what the LLMs are doing, I suspect there's a way of thinking about that in terms of what we think about in terms of the structure of physical space. I certainly think that the sort of quantum LLM, the LLM which has many possible paths that it can follow, that thinking about sort of the quantum LLM, which is kind of normally an LLM says, okay, it has a certain amount of text, it's going to pick the next word, it has a whole ranked list of possible next words, and it will just pick either it'll pick some word that's one of the top words. That's usually a little bit with a bit of randomness. It'll pick the next word and it'll go on and pick the next word after it runs again, and so on. But you can imagine what we would call in our physics project a multi-way system that shows all the possible choices of words at this step, then they lead to new choices of words at the next step, and so on. And that's kind of like a quantum LLM. And you can ask questions about sort of what's the relationship between different quantum branches. In our physics project, we have this idea of branchial space, this thing that relates kind of the different possible branches of history of the universe. And I suspect that those kinds of ideas can be applied to LLMs, and maybe some folks at our summer school here will do that. And so, yes, I think that that's an interesting thing. But I mean, it's been kind of I would say maybe in the future it will be seen as a bit of embarrassment that there was a 2,000-year hiatus between sort of Aristotle studying the kind of global structure of meaning and knowledge and what we kind of got forced to study, because we can see that LLMs somehow do some of this stuff. But kind of going in and saying, what's the natural science? It's like, what are the kinds of questions you can ask? I mean, you can, in many areas, one of the things that's most important in launching a science is knowing sort of what basic question you can ask. Like, for example, natural history, 1800s. It's like there are all these different kinds of critters. Maybe, I don't know how many were known then, hundreds of thousands. Nowadays, it's millions of different kinds of critters that sort of populate the earth. And then you could say, well, how can we say something scientific about all these critters? You know, they're ones with 4 legs, 6 legs, they're ones with fur, they're ones with, with wings, et cetera, et cetera, et cetera. What is the science that we can say? Now, Linnaeus had already figured out a certain amount of that by being able to classify those different kinds of organisms. But then the sort of big science result was, Darwin and the origin of species and the idea of natural selection and so on. And that was a place where one could now take this just hugely diverse collection of things that one saw and have some general theoretical principle about it. And I think the same kind of thing is what we can expect to see in kind of the whole sort of span of human knowledge that's represented in LLM. Let's see, Luhan asks, also here, to what degree do you think LLMs provide us with insights on the internal working of our brain? Do you think there's more lessons to learn from the structure of the human brain when designing the next generation of LLMs? I think that's an interesting question. And I think that LLMs, I don't think the impact of LLMs is yet fully absorbed in neuroscience. I think in neuroscience, there was always the question, what's important in the brain? You dissect a brain. I've never done it. I've never, I'm always impressed when people say I've held a brain. I'm way too squeamish to ever do something like that. But anyway, brains are full of, 100 billion neurons, human brains at least, and lots of other kinds of cells, and there are all kinds of things happening, and there are all these little dendritic spines, and maybe they twitch, and maybe they have quantum effects, and maybe there's little vesicles of neurotransmitter, and maybe it matters, down to the shapes of the vesicles and so on. What matters in determining this thing we call thinking? Well, I think what LLMs have shown us is something quite surprising in some ways. I mean, I not that unexpected to me, for example, but in general, quite unexpected, that it's all just like neural nets. It's not, there isn't a little twitching quantum spine there. It's really important to being able to do this sort of human activity of being able to generate language or be able to generate certain kinds of linguistically based human thinking. So I think it's a very important data point that there's less, you don't have to worry about, the effect of the glial cells on whether you say this word or that word. You don't have to worry about some kind of quantum effect in the way that the way that grammar of sentences works. That's a really important result. Now, how do you go on from there? Well, it's not clear that, studying an LLM is a lot easier than studying a brain. Brains, we don't yet have the way to record from individual neurons. With humans, we don't get to do that anyway, because we don't really want to, untangle our brains, so to speak. It's a thing where we get to see what's going on much more clearly. And then the question is, how similar are the phenomena that happen in LLMs to ones in brains? It seems to me they're very similar. There are a lot of things about the way learning works, spaced repetition as a strategy for human learning, for LLM learning, lots of kinds of things about the ways things forget, the ways things learn from few examples and so on. These are very human-like. There are very many phenomena here that seem to be very human-like. Now, when it comes to human psychology, and whether you take, a Freud level, superegos and so on theory or something else, the analog of that, AI psychology, is a field that doesn't exist yet, but it will. And there will be sort of a global understanding of the psychology of AIs, just as there's some level of global understanding of human psychology. I think the real challenge for both neuroscience and LLM science is sort of the same challenge, which is, in neuroscience, what the individual neurons are doing. In LLM science, what the individual neurons are doing. The question is there a higher level description of what's going on below the level of just, well, the LLM says this or the person says this? Is there a kind of a narrative science that can be made at an intermediate level in both neuroscience and LLM science? LLMs give us a big leg up on being able to do that. They don't give us a kind of slam dunk result, because they have the same issues as brains have. There's lots of neurons, there are lots of things, they're doing a lot of different things. They have the potential, they expose the natural science to us in a better way. Now, I have to say, one could imagine a natural science of computers as well. People usually don't do that. You run a computer, and it does what it does, and you're looking for particular output. But when you say, let me, like for example, back in the day, I don't know whether it still works, but you could take an old analog radio and you could put it next to a computer and you would hear it going, you know, all kinds of sounds as it picked up various kinds of electronic emissions from the computer. And that would be something where you could that was a way in which sort of there's telemetry from what's happening inside the computer. And you could imagine a natural science where you could say, I recognize that what the computer is doing, it is generally doing this because I can hear this weird sound. Most of the time one doesn't do that with computers. Most of the time that's not how one thinks about using computers. My own efforts in kind of studying simple programs and what they do are much closer to a natural science of computation, of just seeing what happens in a computer. And there's a certain amount one can say there, these different classes of cellular automata, of behavior in general, all these kinds of things. But that's sort of a different story. But no, I think, I mean, in terms of whether there is inspiration from brains for LLMs, I suspect the answer is yes. I suspect that there are some sort of hardware features of brains where we get to, you know, learn as we think type thing, rather than having to have a separate training phase from a thinking phase, so to speak. Now, whether we really learn as you know, whether that really works, or whether we're just buffering things up, and then, you know, maybe when we're asleep we reconstruct the memory structure, it isn't really known. But there probably are some things we can learn from kind of the human brain case that are relevant to LLMs. I think we've already, you know, the big thing we've learned is we just took the output of lots of brains and we fed that in as the training data for the LLMs. Let's see. Zombor asks also here, does the spread of LLMs incentivize scientists and humans in general to become more deeply specialized, to outcompete LLMs in a narrow domain, or to become more broadly spread in order to creatively generate connections between apparently remote domains? I strongly think that there will be a push for more generalists than specialists in the future. I think that LLMs and AI in general, computation in general, computational knowledge just makes it possible to get specialized things done much more automatically and efficiently than we've been able to do before. And the things that are still for us humans is the choice of what do we want to do. And that's really a much more generalist kind of thing, where you have to know about all these different things to say, I want to go in this direction. I want to start investigating LLM science, rather than just, well, I'm in an electrical engineering department, I'm going to study electrical engineering, so to speak. You know, this choice of what to do is something for which one has to have kind of broad knowledge. So I really think that's the direction that things will go. We're getting all kinds of funky things here. Brad is asking, will it be possible to use LLMs to achieve world peace? Or if world peace isn't big enough, can we beam LLM chats into outer space to try to get universal peace? I think that's wild. You know, I think this question of sort of, you know, how do we keep the humans happy and prevent them from fighting with each other? You know, one of the issues is scarce resources. And the question is, if one feature of computation is, it's not scarce. There's sort of infinite computational universe that you can mine, and there's an infinite amount of stuff out there, and you're not going to run out of computation. There's always more there. You don't have to worry about running out. It's not like, hunting squids or something, and the squids, you run out of squids. You end up with, the computation is an infinite resource available to everybody. But there's still always some sort of scarcity. For example, there's scarcity in physical space. We're on this planet. Well, maybe we can go hang out on other planets as well. But there's also scarcity, conceptual scarcity, like, are you the first person who gets to the peak of Mount Everest or whatever else? Are you the first whatever? That sort of by definition is a scarce thing. Now, then the only question is, well, of these scarce things, what do we actually care about? Maybe you can say, I was the person who got the very first copy of this book that came off the print run. people don't usually care that much about that unless it's an antiquarian book in a very special situation. People don't, there's some things people care about, there's some things people don't care about. Sort of defining what people care about is sort of what defines what counts as scarce. And I suspect that's the, when there are conflicts, maybe we're just built to have conflicts, because after all, for the history of biological evolution, it was, as Darwin put it, the survival of the fittest in the struggle for life, so to speak. We've had 2.6 billion years or 3 billion years or whatever it is of habituation to conflict, and maybe that's part of the human condition, just as kind of the seeking the new and not wanting things to get too easy is part of that. So I think it's kind of a I'm not sure whether that's part of the human condition. You say, well, let's get rid of that. Let's remove that part of the human condition. Well, again, it's a be careful what you wish for type thing, because maybe by removing that part of the human condition and saying everybody's going to be peaceful all the time, it's like everybody's kind of the drone all the time, and that's kind of the end of history and so on. But I think so I'm not. I wouldn't count on given the human condition, I wouldn't count on LLMs being kind of or AIs in general. There might be situations in which okay, as a practical person existing in the world, running companies, things like this, I often see situations where it's kind of like, it looks like there's two things that are just in total conflict, but then you have to have an idea. And when you have that idea, suddenly there isn't a conflict and everybody's happy and it's all good, but you have to have that idea. And so insofar as it's a question of how can you best have that idea, that's a place where sort of intellectual things and AIs can potentially help. Is there a solution to every human problem? Well, my guess is there's scarcity and so on, where there sort of by definition won't be an ultimate solution, but it's perhaps the case that there are more creative things that can be done, and maybe the AIs will help with that. Let's see. There was a question from Hengwan. What do you think of power laws? Do you think there are some sort of good entry points for explaining the principles behind power laws? So just to remind people, power laws are things like, I don't know, a very, very famous one is if you rank the words in English in order of the frequency with which they occur. So the word the, in spoken text, people always say I is the most common word. I'm not sure if that's really true, but the and a and so on, they're pretty common words. Rhinoceros is less common. Something like anti-disestablishmentarianism is probably even less common. You can kind of rank the words in order of the frequency with which they occur. And there's an observation that the nth most common word has frequency about 1/n. So that's an example of a power law. It's that's a pretty common example. There's a bunch of similar things with the distribution of incomes or something. If you rank them in a country, you'll see the same kind of distribution and so on. Different power law, but same kind of idea. The question, why does this occur? I don't think I really know. I mean, there are a lot of power laws, even in LLMs, there are power laws. There are some sort of restricted cases where you can see why it has to be that way. But I would say as a sort of the general source of power laws, I don't think I have a very good answer to that. There have been various efforts to answer that. My guess is that in the end, and I haven't thought this through properly, my guess is in the end, the power laws exist because of the way that the kinds of observations that we choose to make and the kinds of things that we choose to measure, so to speak, lead inexorably to that. But I'm not sure about that. It's a good question. Michael, also in person, asks, what do you think of the future of AI in video games? They can be used to control the actions and dialogues of NPCs. I guess that's non-player characters. The design of the game's world and even the design of assets on the fly using little data. But let's see. Video game assets take up a lot of data. We could use AIs to generate assets on the fly, cut down the download size of games as well as the effort needed to make assets. For sure, absolutely going to happen. I mean, using, there have been experiments on this for 25 years or more of games where there's sort of generative, procedurally generated scenery. That's been a thing for 30 years or more. The idea of sort of procedurally generated characters is a thing that, and procedurally generated actions, for sure, that's a thing. And being able to have sort of more and more sophisticated, realistic scenery generated by generative AI, more and more realistic kinds of behaviors on the part of agents in the game, for sure. I mean, I think that's a thing. And now the only question is, at what point do you care whether the thing you're battling is another human or an AI? At what point do you say, you know, I'm having a good enough experience without any humans in the game, so to speak, where it's a pure AI? Now, obviously, there are games where there aren't other humans, but there are many multiplayer games and virtual worlds and so on, where people are really sort of seem to be very interested in the fact that there are other actual humans in the picture. But I think an interesting question might be, at what point do you not care whether the thing that you're interacting with is a human or an AI? And that will come up also for tutoring in education. It will come up for various kinds of therapy and so on, where you're talking to your AI therapist or you're talking to a human therapist. And do you care whether the thing that you're chatting with is a human with sort of human empathy, or is it enough for it to be an AI with AI empathy? And my guess is that in many applications, people will in fact get to the point where they're okay with the AI. I'm not sure about this. I mean, I think it's a question of let's take education as an example. Will it be important that you're sort of convincing the human, and the human is convincing you of something in education, and the human is recognizing that you learned something? Or will it be enough that you have sort of gamified education where it's merely an AI, merely badges that are invented by the AI that make you feel like you're making progress? I'm not sure. See, we have a lot of stuff here, and we shouldn't go on too much longer, but it's let's see. Yeah, Danielle is asking, how might we be able in the future to tell what we're seeing on screen isn't AI generated? Anything we could do today? She says, I think you might be a bot. So that's an interesting question. I think that the kind of the provenance of things that we experience will become more important. You know, people have looked to blockchain as a way to kind of record the provenance of what you're seeing. Where did that come from? I mean, I know that sometimes when for ages, when I've looked at science, technology things, I'll say, where did that come from? It helps me understand sort of the context of what's going on. Who were those people? Where did they learn what they're going to say here? You know, perhaps we can expect to see more kind of the provenance of, oh, this person showed up and they're on a live stream and they're doing this, that, and the other. But actually, we know that person has continuity with the person who walked into the room to do the live stream and so on. You know, those kinds of provenance, historical provenance and information will probably become more significant there, and more to the kind of, you know, is it an AI? Now, you know, as we think about kind of the principles of AIs, you know, there are, I've kind of imagined this world in which we have to define, you know, there are 200 principles you might pick about how AIs work, which might not be compatible with each other. And it's kind of like people might have giant placards for, you know, principle 11 or principle 75 or something like this. But one of the principles, along with things like must every AI have an owner, is must AI declare itself? Must you have to say, this thing is AI generated? Now, that's a complicated thing, because it's kind of like saying this thing was made in Italy. What does it mean this thing was made in Italy? You know, does it mean that every sort of, you know, every atom of this thing sort of came from Italy recently? Or does it mean that the final assembly happened in Italy? Or does it mean that the designer was in Italy? You know, there are sort of rules about that in various kinds of trade setups. But, you know, that's a question for AI. Does it, you know, if you Photoshop the background, is it AI? If you had, you know, this or that thing, is it AI? Probably it will be worthwhile to have sort of a well-defined collection, a hierarchy of sort of levels of AI-ness. Just like for self-driving cars, there's kind of a notion of these different levels of self-drivingness up to, you know, the level 5 you can sit in the back and just hang out and do something different type thing. I think that that's another kind of question of sort of the declaration of AI-ness of things, and perhaps that's one of the principles one might think about following. And does an AI announce itself? Is that one of the principles that we have for AIs? Is AI announce themselves? But it's a complicated, slippery slope, because does it have to announce itself as an AI if it did a spell checking? Does it have to announce itself as an AI if it made up the original concept, but then the rest of it, that was just a prompt for humans, and then the humans wrote the text? Let's see, maybe one or two more things, and then Michael asks, thinking in terms of interconcept space, do you think there is an approach to using technology to develop a way that we may better understand or gain experience to bridge the gap of interconcept space of what we know and what we don't know? That's an interesting question that I've been recently thinking about. To what extent can we get kind of experience of what we don't know about? Now, in a sense, I've been working on those kinds of things for a long time, studying kind of simple programs and what they do, like the thing behind me is an example of something made by a simple program. And the question is, the question is, can we how do we get an understanding of that? If you just plop yourself somewhere into concept space or into kind of rulal space of different kinds of rules, if you plop yourself into that, it's pretty disorienting. It's like, what the heck is this? I haven't seen anything like that before. I think we humans have to have a certain degree of gradualism. We invent a new word. We start thinking in those terms. We invent something else. In mathematics, you see it, we find this theorem. We find another theorem from that theorem, find another theorem from that. We kind of incrementally go from here to there. I think that's kind of a thing that we have to do. And how can we accelerate incrementally going from here to there? Quite possibly, yes, as we have AIs that can help us learn how to learn and tell us what we have to kind of do to learn the next thing. I think that's a thing. But I think this kind of question, let's see, who will write the textbooks of interconcept space or some random part of rulal space? That textbook has to go lily pad to lily pad, so to speak. It doesn't get to be the alien textbook that's just out there in that's why the extraterrestrials, so to speak, that's why alien intelligence is kind of a hard concept to deal with, because it's like, by the time it's alien enough, it just doesn't relate to us. We just can't sort of communicate. We can't map our version of intelligence onto its version of intelligence. I think yeah, so this question of how do we expand our kind of domain in rulal space? How do we learn what we don't know about? The first thing we have to do is recognize that there's stuff out there that we don't know about. That's a big part of my new kind of science effort and rulology and studying what simple programs do. Is yes, there's a lot of stuff out there. Now there's a question of, do we care about it? Can we, for example, make technology that we think is cool and useful based on exploring those kinds of things? And that's kind of a long time challenge of mine. Let's see. Just going to I'm being told I need to get going in a moment, but okay, maybe we end with this. David, who's here, says, when will the statement, "I think you might be a bot," be a compliment rather than a criticism or an insult? That's an interesting question. I think in if I imagine doing some computational kind of thing, if I imagine doing some manual task, I'm learning how to do some very precisely crafted thing. I'm making a a beautiful kind of thing that is very precise, or I'm landing a plane in a very precise way, and somebody says, you know, boy, was that landing done on autopilot? You know, in a sense, perhaps already that's a compliment, so to speak, in that case, that you achieved something that was beyond the level of sort of messiness that we humans normally achieve. I think when it comes to kind of, you know, that was an idea, that was an intellectual development that was so impressive that it must have been this kind of, you know, this LLM that knew about all these different areas and managed to pull them together. You know, wow, you're as good as an LLM, so to speak. Yeah, that might become a compliment one day. I think it's you know, that's a real question of kind of a lot about the future of humanity, and a lot about what we, you know, what we aspire to, because there are a lot of things where, you know, we might aspire to being able to do this or that thing, and you know, then it turns out it's actually easy to do that. There's actually technology that makes it easy to do that, and then we're like, that doesn't matter. We're interested in this other thing that is still hard to do. And I'm trying to think of an example where people have well, like for example, being able to run really fast, you know, being able to go really fast by running really fast. Back in the day, it was surely a very significant thing. I mean, it's still significant, but it's not as significant to be able to be the fastest possible runner, because you know what, you can get in a car and go much faster than just running. And so it isn't as much a kind of a badge of honor to be able to do that. Now, for us today, there has been, well, it's sort of a dramatic thing that's happened with LLMs. For a while, it's kind of being able to spin up an essay about something, being able to write the legal brief, being able to write this kind of explanation of something. That was a kind of badge of human honor, but it is becoming less so because LLMs can do that now. And, you know, there are other things that LLMs can't do that are still, so these things that get automated, they might have seemed significant in the past. Another good example would be calligraphy and being able to make sort of very elegantly presented kind of written things. It's like that was a big deal until there were fonts and so on. It's still a cool thing to be able to do, but it's not nearly the kind of big deal that it was in the past. And I think that will, you know, as we define what we think is significant, that will be defining it to be those things that aren't the things that technology makes easy. And I claim one of the things that will be inevitably not made easy by technology is the choice of what it is we decide to do, which technology doesn't have an intrinsic way to figure out. And so that's kind of a thing that is intrinsically human, because the general case of the general Ruliad that does everything is sort of the case of nothing. And insofar as we sort of have an existence as humans, it's these choices that we make that are significant. And as I said, I think that the, you know, you did that as well as a bot will be something that for particularly as these things transition from being things that only humans can do, and humans aspire to do them better and better and better, and then the bot does them really, really well, it will be for a while, at least a compliment to say, you know, you did that as well as a bot. So, okay, with that, I should probably wrap up here. And, you know, in the future, somebody can, you know, use this live stream as a piece of training data for a bot of the future, and can be amused by this. The bot can be suitably amused by my statements about, you know, the compliments of you did it as well as a bot. All right, thanks, and bye to people on the live stream. And thanks for being here in person, guys. And boy, that's a new and different thing. I've actually got to, okay, thanks.